In this video, I'll show you how to integrate using inverse trigonometric substitution. This is question 4 in the series. The function that we'll be integrating in this video looks like this. And to be successful at integrating this function, you'll need to know some of these useful identities. Namely, this one right here, where we have the square root of a to the power of 2 minus x squared. Notice that in our function, we have something that matches that. Our a value for our function would be 5, because 5 to the power of 2 is 25, and minus x squared is also found right here. If your function matches this expression, you have to set your x equal to a times sine theta. So let's do that to start. X is equal to a, which is 5, times sine theta. The next step is to take the derivative of this function. And if we derive this function, we end up with dx is equal to 5 cosine theta, because that's the derivative of sine theta, it's cosine, d theta. We now have two replacements. We can replace the x, and we can also replace the dx, where our function becomes totally in terms of theta. Here's what I mean. The integral of the square root of 25, that part hasn't changed, minus this, because we're going to replace x with this, 5 sine theta to the power of 2, and we will also replace dx with 5 cosine theta d theta. What I'll do next is simplify this expression as much as I can. So for the most part, it stays the same, that stays the same, but this too will be distributed to the 5 and to the sine theta, where we end up with minus 25 sine squared theta times 5 times cosine theta d theta. And at the same time, I will take this 5 outside of the integral. So I have 5, the integral, and similarly, I will factor out a 25 from these two terms. If I factor out a 25, I'm just going to show you my work right here. I end up with 25 bracket 1 minus sine squared theta. Notice that if I pull out a 25 from both of these terms, I end up with this. And of course, don't forget the radical. And now that we have a product underneath the radical, 25 times this thing, I can separate these two components. Watch. The square root of 25 and the square root of 1 minus sine squared theta. And I'll do that. If I square root 25, I end up with another 5. And I'm left with 1 minus sine squared theta times cosine theta d theta. My next step is to use an identity. And I can use an identity right here. 1 minus sine squared theta. What does that remind you of? Do you remember this? Cosine squared theta plus sine squared theta is equal to 1. Well, if I bring this sign over, I end up with cosine squared theta is equal to 1 minus sine squared theta. So I can replace this now with cosine squared theta and then square root it, where I end up with simply cosine. If I do all of that, I end up with, and of course taking this outside, gives me 25, the integral of the square root of cosine squared theta, which gives me cosine theta, times cosine theta d theta. These two can be multiplied together, and if you multiply them together without having to rewrite everything, we end up with cosine squared theta d theta. Now we have to integrate cosine squared theta d theta. And the best way to do that is to use half-angle identities. And I do have several videos dedicated to how to use half-angle identities to integrate trigonometric functions, so make sure you view them. If I replace this with the following, I end up with this. 25, the integral of half 1 plus cosine 2 theta d theta. This part still hasn't changed. I'll pull out this half, and if I do that, I end up with 25 divided by 2. I'll leave it as a fraction, 25 over 2. the integral of 1 plus cosine 2 theta d theta. Now this function isn't a walk in the park. We still need to integrate the 1 and the cosine 2 theta. 1 is the easy part. We know that the integral of 1 is simply theta. So let's do that. 25 over 2, and we found the integral of 1 and it's theta. And if we find the integral, we don't need to put this around it. So I'll pull that out. Plus the integral now of cosine 2 theta d theta. This is a double angle, and we will need to use u-substitution. We'll have to set u is equal to 2 theta, and we'll have to take the derivative of both sides where we have du is equal to 2 theta becomes simply 2 d theta. And we'll substitute this back into here. And without having to show all our work, I'll just do it on the side. We have the integral of cosine u, and d theta can be manipulated here as simply du over 2. Notice what I did is I isolated for d theta by dividing both sides by 2, and then I replaced that expression into here. And this is not hard to integrate now. Pull out the 1 over 2. The integral of cosine u is simply sine u. So instead of having to write that all in, we have sine u plus c. And put this back here where we have half sine 2 theta plus c. So I'm going to replace this now with the following, where I have 25 over 2 bracket theta plus half sine 2 theta plus c. What I'll do next is multiply this 25 over 2 into my expression. And if I do that successfully, I end up with, now this part is going to be easy. We have to write this expression in terms of x because that's what it was originally. So let's go ahead and do that. Remember what we set our x equal to? We set it equal to 5 sine theta. So remember that. Let's write that down. If we isolate for theta, we end up with x over 5 sine theta. Take the inverse of both sides. Sine inverse of x over 5, and we have simply theta. So we can replace this with that. Sine inverse of x over 5. Now this part is the tricky part, and at the beginning we were told that this is a helpful identity, a double angle identity, where sine 2 theta is equal to 2 times sine times cosine. So let's use that instead of this. Plus 25 over 4, 2 sine theta cosine theta plus c. And now what we can do is replace these thetas with this. Now of course, sine, if we were to take a look at sine in a right triangle, sine is opposite over hypotenuse. So our opposite is x and our hypotenuse is 5. So if we were to take the sine, we would end up with simply x over 5. So this right here is equal to x over 5 as shown. So this is gone. But now we have to take it in terms of cosine. And cosine is adjacent over the hypotenuse. The adjacent here will simply be, well, we have to use the Pythagorean theorem. A squared plus b squared is equal to c squared. These represent the legs, so a and b. Let's call that b. 5 to the power of 2 is 25, plus our adjacent. Bring this over. We have 25 minus x squared. And we square root both sides. We have 25 over x squared. So if we were to take cosine of this triangle, we have the adjacent, which is equal to that, over the hypotenuse, which is 5. So x over 5 times the square root of 25 minus x squared over 5 times 2 times 25 over 4 plus c plus this expression. For our final step, you can simplify this expression, and let's do that. 25 over 2 sine inverse of x over 5. Cleaning all of this up, this becomes a 2, that becomes nothing. 25 divided by 5 is equal to 5 half times the square root of 25 minus x squared plus c. And what I'll highlight is your final answer. And so there you have it. That is how to integrate using inverse trigonometric substitution. Make sure to watch question 5 of this series where we focus on an example with definite integrals.